Chemical formulas. So we represent compounds with chemical formulas. It's kind of a shorthand. The chemical formula tells us which elements are present in that compound and the relative number of atoms or ions of each of them. And we do this with the element symbols and numerical subscripts. So the subscript follows the element symbol and tells us how many atoms. So water we represent as H2O. H is the chemical symbol for hydrogen, followed by a subscript 2. So this tells us 2 atoms of hydrogen, and then we have the symbol for oxygen. We'll find kind of as a little minor theme that chemists avoid using the number 1. So this is H2O. We don't write H2O1. Why? Well, why write a 1 if you don't need to? If there were 0 oxygens, I wouldn't write the element symbol at all. And if there was more than 1, I would write some other number. So we just do H2O. Carbon tetrachloride is carbon, no subscript. That tells us there's 1 carbon atom. And Cl4, that tells us there are 4 chlorine atoms. Now this is where you have to be a little careful with when you're looking at these letters. Because this guy right here kind of looks like, well, that could be C capital I, right? Lowercase l's, the number 1, and capital I's often look the same. What's that? Whatever you say, I can make it the other, right? So this is how I represent 1. Just straight line, that's 1. This is capital I. Put the bars on top to say, hey, this is an I, not a 1. And then lowercase l, I'll actually make a script L so that it doesn't look like a 1. So when you're looking at something that's typed, you have to look at the font and make sure you understand what you're looking at. Now, what is the clue? What might be a clue that this is not carbon-carbon iodine?
You would have a 2 at the end.
Right. If it was carbon-carbon iodine, we would write C2I4, right? So that's your clue that, oh, wait a minute, maybe this is chlorine instead. So occasionally things can be confusing like that. So just be aware. Chemists, scientists in general, we like to take things and like to categorize them, put them into different groups. Okay, so we've already categorized ionic and covalent bonds, and now we're categorizing types of formulas for chemicals. So 3 different categories: empirical formulas, molecular formulas, and structural formulas. What are they? An empirical formula gives the relative number of atoms of each element. Empirical means from experiment. So that's one type of formula. A molecular formula gives the actual number of atoms. So how is this different? Well, if we look at this compound, C4H8, this is not the simplest ratio of carbon to hydrogen. There's a common factor in these subscripts of 4. So the simplest ratio, the relative numbers, would be 1 carbon to 2 hydrogens. So C4H8, if you think of it as a fraction, can be simplified. Empirical formulas give the lowest ratio. So we can think of 4 to 8, right? That's a ratio that can be simplified into 1 to 2. It's the relative numbers. There are 2 hydrogens for every 1 carbon. The molecular formula gives the actual number. So this is a molecular formula, and this is the empirical formula. B2H6. 2 to 6 can also be simplified to 1 to 3. So the empirical formula is BH3, the molecular formula is B2H6. Sometimes the empirical and molecular formulas are the same. CCl4, that's a ratio of 1 to 4. You can't simplify that. The empirical formula is the same as the molecular formula. Any questions? Other than, why do we do this? The other type is a structural formula. Structural formula uses lines to represent the covalent bonds, and it shows how those atoms are actually connected to each other. Empirical and molecular formula just says what's in the molecule or the ratio, doesn't say how those things are connected. Structural formula gives a little more information. We use a single line for single bonds, a double line for double bonds, and a triple line for triple bonds. And we will learn a lot more about these different types of bonds. The structural formula for H2O2 can be written like this. We've got hydrogen with a single bond to oxygen, that oxygen with a single bond to another oxygen, and this one with a single bond to a hydrogen. Could you arrange those 4 atoms in another way, at least on paper? Sure, you could. I mean, you could maybe mix it up and draw it like that. That's not how it is, but you can imagine. You could put an oxygen in the middle and put everybody else around it. So connected in different ways. The structural formula tells you how the atoms are connected. These two made-up things that actually do not exist would have the same molecular formula, but they would be different things. Is there, okay, so if this is the molecular formula, H2O2, what's the empirical formula for that compound? HO. The empirical formula would be HO. That just tells us the ratio. We use different formulas at different times. Basically, depending on how much information either we know about the compound or how much information we want to communicate about the compound. The structural formula gives us the most information, and the empirical formula gives us the least. So let's write the empirical formulas for these compounds. C5H12, what's the empirical formula? It's just C5H12. A ratio of 5 to 12 cannot be simplified. How about Hg2Cl2? HgCl. The ratio of 2 to 2 is simplified to 1 to 1. How about this guy? C2H4O2. CH2O. Great. You guys are all awake. You're getting it. Okay, so 2 to 4 to 2 simplifies 1 to 2 to 1. Another way to represent compounds is using molecular models. And we have several different types of models. Ball and stick molecular models uses balls to represent the atoms and sticks to represent the bonds. And we can put them together in a way that not only shows how they're connected, like the structural formula does, but how they're arranged in three-dimensional space, so the shape of it. And we often color code the balls to specific elements. You do not need to memorize these colors, but they're just here for reference. And you'll see as we go through, looking at these PowerPoint slides, that these are the colors that are commonly used when they show you the pictures. And so we've already seen pictures of carbon monoxide, carbon dioxide, where we've had the black balls and the red balls, and water where we've got red and white, and we use those consistently to represent different elements. Another type of model is a space-filling model, and this gives us a better idea of the true shape. It's our best estimate of how an atom or a molecule might look if we could actually get in and see it. So here we see these different representations. Molecular formula, structural formula showing how they're connected, a ball and stick model, The nice thing about this is you can very clearly see how things are connected and you get the shape. Those are hard to draw though. And then the space filling model. These are more accurate, but they're not as easy to look at as the ball and stick model because everything kind of just blobs together. But this gives us a better representation of what the molecule actually looks like. There's not really a big gap here between the carbon and the hydrogen. They're actually smushed right onto each other, like Play-Doh globs or something smushed together. Here's a table from your book just showing these different representations for several different compounds. When you get to something more complicated like glucose or benzene, the space-filling model is a little hard to see even what atoms are on the inside.